Chemistry 3.1 Quantitative Analysis. This unit is about titration. Use these to figure out the concentration of a substance by using a substance with an already known concentration. This is Timmy. Timmy is a car. Timmy lives in a parking lot. His lot has 6 rows with 12 parking spots per row. Across the road, he sees another parking lot. The lot holds the same number of cars as this one does, but only has 4 rows. Using his calculator, Timmy dropped out of car school, Timmy can figure out his 72 spots in his parking lot. As the parking lot on the other side of the road can hold the same amount of cars, there's the same amount of spots. By dividing spots by rows, he gets 18 spots per row. If we label spots as N, spots per row as C, and rows as V, we get this triangle formula. N equals C times V, C equals N divided by V, and V equals N divided by C. This is how titrations actually work. We normally put an acid in the flask and the base in this long burette thingy. We'll also put an indicator here which will tell you when the titration has reached its endpoint, in this case when the liquid will turn pink, so then the moles are matching. One of the substances, in this case the acid, has a known concentration, which is moles per liter, or spots per row in the parking lot example. Using this info, we can figure out the concentration of the other substance, or the other parking lot's spot per row. The letter N means moles, letter C is concentration, the letter V is volume. Obviously, these numbers are ridiculous. You'll never use 6 or 4 liters in order to test for something, and I think 12 moles per liter of hydrochloric acid would burn to the touch. They were just there for ease of calculation and matching with the parking lot example. Now imagine that the parking lot across the road can fit 2 cars in one spot. Now, they still hold the same number of cars, but they only need half the slots. To find the spots using a ratio, you would multiply by the ratio, with the number on the original side being the denominator, in this case 2, and the number on the result side being the numerator. That's the y. Through this, we can figure out the spots per row, which is 36, and then, or 36 spots, which is 9 spots per row. In the titration example, we can see that in the original reaction, for every 1 calcium carbonate, the no number means 1, you would need 2 hydrochloric acid, which makes the ratio 1 to 2, which means you do the same thing, as if 2 cars would fit in 1 parking spot. And here's a much more complicated example. An average of 18.55 KMnO4 was required to meet the endpoint of a titration with a standard aqueous solution of the oxalic acid. The concentration of the oxalic acid is 0.015 moles per liter. The volume of the oxalic acid was 25 milliliters. And then there's the simple equation. Figure out the concentration of the MnO4. First off, I can see 3 numbers, 2 of which are volumes in milliliters, and 1 of which is a concentration, which is in moles per liter. I can also see a mole ratio of 2 to 5. Here's a table with all of our values in there. We have the mole ratio up at the top, and we also have 2 volumes and the concentration. This looks a little cleaner to me, so I'll put it in this format. They're the same numbers, and you can expand it back by just multiplying those 2 numbers together. Here's a visualized parking lot with 25 rows and 15 spots per row. They are decimals, so they go backwards and multiply together. It'll give us 33.75 times 10 to the negative 4 moles. In our parking lot, there are 5 cars in one spot, and it fits 2 cars in the other. So using the mole ratio, we find 1.5 times 10 to the negative 4 mole. Once again, using the triangle formula, we find the concentration, which is 8.06 times 10 to the negative 3 moles per liter. And that's our answer. Back titration is a little more complicated, but the outcome is still the same. Let's say now that the parking lot has a limited amount of cars it can hold, not only has 2 rows. Luckily, a builder builds a new lot that can hold exactly the amount of cars left. This one has 2 rows and 18 slots per row. Using a similar table, we can figure out that the new one has 36 spots. This means that 36 spots of the original car park still had cars in it after the limited one was full. This means that we can find out the amount of empty spots after the limited one was full by subtracting 36 from 72, and how many spots the limited one has, which is 36. Because that empty becomes full in the limited one. From there, we can figure out how many spots the limited one has. An example of this is with aspirin. We crush the aspirin tablet and dissolve it with a known amount of excess sodium hydroxide. That's fine. The aspirin will react with some of the sodium hydroxide. Not all of the sodium hydroxide is used, some of it is left over, remaining. We now do a titration with hydrochloric acid and figure out the moles here. Go around, you can find the moles per liter over here. And when using ratios, because right now it's 1:1, if it were something different, this is where you would use the converting. Here's a more complicated question for back titration. A 10 milliliter sample of this wine was diluted to 100 milliliters in a volumetric flask. A 2 milliliter sample of this diluted wine was added to 10 milliliters of the 0.05 moles per liter acidified potassium dichromate solution. The mixture was heated so that the ethanol in the wine is oxidized to ethanoic acid. And there's the symbol equation. Excess potassium iodide was added so that any remaining dichromate reacted with the iodide to produce iodine. The iodine produced was then titrated with standard 0.100 moles per liter sodium thiosulfate solution. The average titer volume was 11.45 milliliters. Find the original concentration of the ethanol in the wine. Let's look for values first. First we have two volumes and a concentration. And in the third paragraph, there's a volume and a concentration. There's two ratios, one that's 3:2 and one that's a little bit more complicated. Since these values aren't in the same equation, we have to bring in something that is. Using iodine, we can figure out both substances' ratio to iodine, and then from there, we can figure out their ratio to each other. This ratio being 1 to 6. We also have these two values, which we'll get back to, but they aren't important in the moment. It's top two. Here's a table of our known values, and then here's a cleaned up. First, we can find the moles of the dichromate and the thiosulfate using N equals CV. From there, we can find out the remaining moles of the dichromate by using the mole ratio. From there. And then you can find the reacted moles by subtracting that to that. And then you can find the moles of the ethanol. From there, you can find the concentration of the ethanol. Boom, simple. Now the question specified the original concentration as the 10 milliliter sample of wine was diluted into 100 milliliters. We can multiply the concentration by the conversion rate, which is 10, to get our final concentration, which is 2.31 moles per liter, which is already simplified. Problems with two or more unknowns. It's big boy time now. You have to use other cold chemistry rules to solve these types of problems. Let's go through an example. Two identical 5-gram solutions of an anhydrous mixture containing barium chloride, magnesium chloride, and barium nitrate are weighed out. The first sample was dissolved in distilled water and excess of dilute sulfuric acid was added. The resulting precipitate was filtered, washed, and dried. It weighed 3.93 grams. The second sample was made up to 250 milliliters of distilled water in a volumetric flask. 25 milliliter aqueous were titrated with 0.231 moles per liter silver nitrate solution. The average titer volume was 21.24 milliliters. What was the percentage composition by the mass of the mixture? Firstly, let's use another triangle formula. Mass equals moles multiplied by molar mass. The molar mass of these three substances are already known, as they're just referred to the atomic structure of the compound. Now the mass of all three substances is 5 grams, as stated in the question. Multiplying molar mass of all three by the moles of all three would get us the mass of all three, which is 5. So the molar mass of barium chloride, for example, is 203.8 grams per mole multiplied by the moles, which I put as F, Y, and Z. We get this equation, which will give us 5 grams. N times M equals M. Now for the figuring out stuff. This is that sulfuric acid is added to the mixture. Looking at the